Okay, good. I refer to the PowerPoint here. I just want to make a recap. Okay, here, I'm sorry, it's the old version, which is still here because it's in the cache. So let me just try to download it again. It's in the cache of, if you download it from the website, it's the right one. But here, let me see if I can take the right one. Otherwise, I find another way to find it. Let me see. Still, it's not good. There are not the figures here. Yeah, 1 second. I need to find another way to download it. So let me go with Firefox. Maybe Firefox is updating it. Or another browser. Let's see. Okay, I think this is the good one. Let's see. Okay, this is the good one. Okay, good. Now, let me check. I need to close this. And this one is correct. Okay, I hope also remotely you can see it. So, InfoGap. I want to show you this slide once again, because I think it's important to make sure that you understood here the reasoning. And the reasoning is that we have, from, for instance, a climate model, a future prediction, maybe a climate model, maybe hydrological modeling cascade to a climate model. We have a future prediction. And here, the example refers in particular, as you may remember, to a future prediction of water resources availability. And this future prediction is accompanied by an estimate of an error. This estimate is purely a guess. And this estimate of the error is S. So our future prediction is X hat. And here I indicate with X the reality. So what we will see actually in the future. So the reality will differ from the prediction. X minus X hat is the error, the prediction error that we realize only once we see the future. And we have an estimate which is, again, purely a guess, an estimate S of the error. For instance, climate models give to you an ensemble of predictions. So you have, for instance, for temperature, ensemble, an envelope of predictions. And it is usual practice to take the average of this envelope as a best prediction. It would be our X hat. And it is usual practice to take the width of this envelope as an estimate of uncertainty, as a possible error, okay? And therefore here, the width of the envelope could be S. S is not a formal estimate. We don't need to estimate S a theoretical model. It may be a guess. So the result is that actually the error that we make, the error that we realize once we see the future, is larger than S. So this, this X minus X hat may be larger than S. And then this ratio in absolute value is larger than 1. If the future error is larger than S, this is possible. And this ratio that you can see here is larger than 1. Okay. And then we can identify, let's say, a cluster a range of X value, which depends on H, by imposing that the relative error in absolute value here is less or equal than a given H value. So the H value may be larger than 1, may be lower than 1, and therefore, basically, H is quantifies our robustness. In a way, if I impose that H is 0, it means that I don't accept any error into the future. I don't accept any uncertainty, which means that our procedure, our prediction, our methodology is not robust. It's not robust against uncertainty. If I put H0, then UH reduces to the only best estimate. H0 means that X is equal to X hat, so the reality is equal to our best prediction. So we don't allow any uncertainty. We have a best prediction X hat, and we want that the real value X is equivalent to X hat, is precisely X hat. And therefore we fix H at 0, which means no uncertainty, which means that our solution is not robust against uncertainty. Not robust because it's not tolerating any error. Robustness, remember, means resilience against uncertainty. It means that the solution works well, even if I have a prediction error. This is robustness. And therefore, UH is an indicator of robustness. So, through this definition of the relative error, then we can define the robustness function. The robustness function, keep in mind, it depends on a critical value of the benefit. It means that I fix on my benefit, in terms of my benefit, a lower value, a low value, which is the minimum that I consider necessary to be my methodology, my procedure, my adaptation successful. So this BC is called a critical value. And this critical value is lower than the benefit value that corresponds to X hat, to the best prediction. Is lower because, I make a best prediction, I optimize my system to give optimal benefit in terms of this prediction, and then I fix a lower value of the benefit, BC, which is lower because it is a critical value for the success of my adaptation, my strategy. And therefore, BC, and it is written in the web page, BC is lower than B tilde. B tilde is the benefit corresponding to X tilde. And BC is lower than B tilde. So now I can define my opportuneness function in terms of H, depending on BC, and it is defined in this way. It is the max H, so it is the max relative error, max H, which ensures that I'm getting a benefit which is larger than the critical one. So again, the robustness function, which I define with H hat, depends on the critical benefit, is the max relative error, is the max uncertainty that still gives to me a benefit that is larger than the critical one. And if this max H is large, it means that I have robustness. So you can understand that if BC goes down, if BC decreases, which means that my critical requirement lowers down, I am expecting a larger uncertainty. So as long as I decrease my minimum requirement for the strategy to be successful, I can tolerate a large uncertainty H, which means that the set of the X is the set of the possible futures is larger. And this can be shown into a function. I can show into a function the progress of H hat, which is the larger uncertainty that I can tolerate depending on BC. And this is the robustness function, which is here. This is the robustness function. You see the benefit BC. I corrected the figure. So you see here for decreasing critical benefit, I get highest robustness. And keep in mind that for H tending to 0, what I get here is a critical benefit that is equivalent to B tilde, the benefit that I get for the best prediction. And this is called the zeroing property. So basically, for the robustness 0, no robustness, I get the value of B tilde, which is the benefit corresponding to the best prediction. This is what I wanted to recall. And now, if you remember, we introduced also the opportuneness function, because the distinguishing feature of InfoGap is that we also consider the opportunity. And the definition of the opportuneness function is just equivalent to the definition of the robustness function, but it's like a dual definition. So let's go into the details. It is the same concept with a dual interpretation. So,
sorry.
Please.
A question about the slide 21. So is it correct to say then that the H? Can you please go to the 21 slide?
Yeah.
The first slide.
This one or this one?
This one. Okay. So the H in the first equation could be H hat. The H that unfolds. The
H in the first equation is a definition. So we define H value, and the independence of this H value, which may be 10 or maybe lower. Depending on this H value, you find the set of the X values that you can tolerate. In the second equation, H hat is the max of H, depending on BC. It's in the first equation, you don't look for the max H. In the first equation, you just fix H, and depending on this definition of H, you identify the range of X that you can tolerate.
Okay, so but what I do in practice is to fix that H as the H hat.
Yeah, and you look for the maximum. So basically, you fix in the second equation, you fix the critical benefit BC, and then you look for the max H, which gives to you a benefit that is greater or equal than the critical one. So basically, there is a search. If you look at the definition of H hat, is the max of H. So basically, you use the first equation, and once that you use the first equation by computing the benefit corresponding to the different axes, to the different values of X, you use the first equation to look for the max. So basically, what you do with the second equation, you fix BC, okay? And then look at the round parentheses. You look, after fixing BC, you look for the X values into UH that, by using the first equation and the computation of the benefit, give to you a benefit that is larger or equal than BC. This is what you do with the second equation. So of course, I mean, once that you fix the critical value of the benefit, you explore several possible x values. And how do you identify these x values? You identify them by looking at UH. So you try several values of H, and you find several possible values of X. And then you identify the benefit given by these several possible values. Sorry, I go back with the slide with the benefit function here. So once that you have the X identified, you compute the benefit, and you look at the minimum benefit, because you want to look for the worst situation. And then you identify the H value, which makes sure that the minimum benefit is still larger than BC. I wanted to recap this to explain again this sequence, because I understand that the math here may be not easy to be understood, but actually, if you look at these two equations, you can get it. Also, there is an exercise in the website. Let me see if it is already linked there. Let me see. No, I didn't put it there. So basically, the exercise is explained here. Is explained here with these figures. Just 1 second. Okay, so basically through this function, it is, if you look at the website, it's explained with more details, and then the robustness function, indeed, here in this figure that you see on the screen now, is computed by making reference to this real benefit function. So this can be repeated. But again, it is important that you understand this definition of uncertainty model and this robustness function here. Not sure I helped you a lot, but if you have a more specific question, I am happy to reply.
Okay, no, thank you. It's a bit more clear.
Okay, now in terms of opportuneness, what I told you is that we have to look for the minimum uncertainty. So we have to look for the minimum H that allows us to reach an opportunity. And to reach an opportunity, we have to identify a dream. And the dream is a benefit which is larger than B hat, okay? So basically, if you look at the opportuneness function here, for zero robustness, as I said, you get a benefit that is about 24. So the question is, under uncertainty, is it possible that I can get a benefit that is larger than 24? Yes, this is possible if you get more water. If you get larger amount of water in the future with respect to the best prediction X hat, you get an higher benefit. And then the question is, the uncertainty that I have in my prediction does allow me to get more water and therefore to get an unexpected opportunity, an unexpected windfall. Yes, the reply is yes, if you get more water than what is predicted. And therefore you need uncertainty, because if your prediction turns out to be correct, you don't get more water. But if the prediction is affected by uncertainty, you may get more water. Okay? And therefore, it means that uncertainty may provide a benefit that is larger than 24. And let's call this value BW. And this is what is explained here. And I'm sorry that I still have this visualization problem. And because on the website, I can tell you, and you checked it last time, is correct. Here, BW is greater than B tilde, which B tilde is greater than BC. And still, when I make the download, it's still I have this visualization problem. So Again, BW is larger than B tilde, and B tilde is 24 in this figure here, and the BW is larger. I have to fix a dream, okay? And then the question is, what is the minimum level of uncertainty that gives to me the opportunity to get this dream, to make this dream come true? And in this case, I'm interested in the lowest level of uncertainty. So I'm looking for the minimum uncertainty. The minimum uncertainty that still allows me to reach the dream, the windfall, okay? And why I'm looking for the minimum uncertainty? Because, of course, I don't want to pursue a dream that requires a high risk. Uncertainty means a risk, because the robustness function tells me that. So basically, I want, in terms of reaching the dream, I want to reach the dream by minimizing the risk. So I have to look for the minimum uncertainty that makes the dream true. And therefore, in this equation here, I will look for the min instead of the max. The min instead of the max here in the definition of H tilde. So let's look at the opportuneness function. Then the opportuneness function, let's call it beta hat, it depends on BW, depends on the dream, and looks at the min uncertainty at the mean H. H is a quantificator of uncertainty, is a quantification of uncertainty, so looks at the mean H, which still gives to me the opportunity in terms of max benefit to be larger or equal than BW. And in fact, you see the red curve, sorry, goes in the domain of the larger benefits, larger than B tilde. Okay, B tilde is 24. Here I'm exploring the domain of the larger benefits, and the opportuneness function tells me the minimum uncertainty, the minimum beta tilde. Look at the vertical axis. The vertical axis is displaying H hat and beta hat. Beta hat, not beta tilde. Sorry. So it's looking at the minimum H, beta hat, that gives to me the possibility to reach, to obtain the windfall. Now, you see that this combination of robustness and opportuneness is a powerful support in decision making, because I may look at the robustness curve to identify what's the max level of uncertainty that I can tolerate. So for instance, let's suppose that BC is 20. Look at the blue curve. If BC, which is the critical benefit, I don't want to take the risk that the critical benefit is lower than 20. My benefit is lower than 20. So I see from the blue curve that the max level of H that I can tolerate, H hat, is 0.6, which means that the relative error in the water resources prediction shouldn't be larger than 0.6. And then in correspondence of H 0.6, which I can tolerate, I look at the opportuneness function. And so what is the windfall, the max windfall that I can obtain? It's about 27, 28 million euros. So basically, you can play with uncertainty with this graph. You can play with uncertainty, estimate what is the max uncertainty that you can tolerate, and then you get an estimate of the max windfall that you may expect. And this is done without a probabilistic estimation of uncertainty. You are just looking at the max uncertainty that you can tolerate. In terms of climate change, I think this method is very relevant because indeed, when dealing with climate change, climate predictions, we don't have an estimate of uncertainty, a rigorous estimate of uncertainty. We have some ensemble prediction depicting an indication, depicting a pure guess, but it's not a probabilistic estimate. So it's here we reverse the usual way of dealing with uncertainty. Usually in engineering, we want to estimate uncertainty in terms of probability. And in risk-based adaptation design, this is what we did. And if we have an estimate of uncertainty, a reliable estimate in terms of probability, then we can use the traditional engineering approach. Here, we revert it. We don't have an estimate of uncertainty. We look at the max uncertainty that we can tolerate. So we start from the benefit. Our reasoning starts from the benefit and goes back to estimate the max uncertainty that I can tolerate. And this is a kind of bottom-up approach. In fact, robust decision-making is a bottom-up approach. It starts from the end of the process and goes back to the models and the theory. And here you see the definition of the opportuneness function. I said it's dual with respect to the definition of the robustness function. In fact, if you go back to the definition of the robustness function, I go back 3 slides, you see that we obtain the definition by substituting max with min. So it's a dual definition, same concept, more or less, but we change min with max. Okay, now the considerations are in this slide, but I already elaborated them. I already made some considerations during my explanation. I want once again to stress that if you want, you can easily try to reproduce this figure. This is the example that I mentioned. So starting from this benefit formula, which depends on X, and using this definition of opportunities, you can, starting from the formula, you can reproduce this red curve. It's very simple. It's just translating into a graph the equation that you see on the top of the screen now. And then by using a simple min-max function in Excel, you can, or in R, you can find the robustness function and the opportuneness function. I did it in Excel actually, and you see, you can recognize the graphs are made in Excel, and you can easily reproduce them. I wanted also to reproduce them with you in the room, but I don't think we have time because we have a couple of hours of lectures. Okay, now let me go back to the PowerPoint. As I said, these considerations are already done, so we can skip these two slides. Just keep in mind the zeroing property, which I mentioned in the web pages. It's explained in detail. And there is also the nesting property. Nesting means that once that you increase the value of H here, I go back with the slides, sorry. Once that you increase the value of H here, you are increasing also the range of X. And the range of X is characterized by the nesting property. It means that if you go from H1 to H2, you are including in each subsequent range UH the previous X values plus some new ones. This is the nesting property. It means for increasing uncertainty, you can tolerate an increasing range of X value. Okay. So let's skip the consideration and now let's move to another method, which is a narrative. So it's not really focusing on the methodology, and this is much easier to be followed. And So I just want to connect this discussion to the previous one. We introduced robust decision making, or let's say robust strategies for making decisions, and we mentioned up to now two methods: robust decision making, and one example is the min-max method. So just looking at the minimization of the damage. Okay, so once that I have uncertainty into the future, I can seek robustness by looking for the solution that minimizes the damage. And then we talked about infogap. Infogap is similar, but looks also at the opportunities. Okay. Now, decision scaling is another bottom-up approach. Bottom-up because it starts from the end of the process. And let's see the difference, and by looking at this figure. Okay, so basically, if we look at the robust decision making, you may remember we talked about 5 steps. It starts from candidate strategies, and then it evaluates the strategies against the scenarios. We said, okay, we have climate predictions, and we evaluate the strategies against the climate predictions, and then we test the vulnerability of these strategies. And we may apply the min-max method in order to identify vulnerability, and then to identify the best strategy. And then we can directly identify the best strategy, or after the vulnerability analysis, we may find that the strategies that we identify are not satisfactory, and then we can continue the process with an iterative approach. In decision scaling, the approach is very similar, but instead of starting from the solution, candidate solutions, it starts from assessing vulnerabilities, like a land is vulnerable to floods. And then it is this vulnerability is tested against future scenarios of climate change. So the vulnerability is increasing, it's decreasing, and how much is increasing? Because as I said several times, there are some situations and some vulnerabilities which are not really much affected by climate changes as predicted by climate models. And therefore, we try to identify whether in decision scaling these vulnerabilities are increased against climate prediction. We may include further information, not only climate models, but decision scaling explicitly mentions further information. And then after we identify the priorities in terms of vulnerability, then we look at strategies to minimize risks to systems. And it is an approach that has in common with robust decision making the robustness. It is an approach that has in common with robust decision making the bottom-up character. It starts from the bottom. It starts from the land, from the people, from the solutions. And the difference is just that robust decision making focuses on a robust approach, doesn't look in its traditional formulation, doesn't look for opportunities. Decision scaling is more general, and decision scaling, when evaluates the future scenarios to assess vulnerabilities, may use infogap, for instance, in order to also look for opportunities. So what is the difference? The difference is that decision scaling is not binded to robustness. It may also look for opportunities, and it starts from vulnerabilities instead of candidate solutions. So you may You may question if the two methods can be incorporated into one single approach. Yes, it's possible. It is certainly possible. It is also certainly possible to integrate robust decision-making to look for opportunities. So you may ask why then these methods are not combined. The reply is very simple. These methods for decision-making have been developed at the same time in the past 20 years and have been developed by scientists working in different fields. These different fields are all related to climate because there has been substantial renewed interest in decision-making after climate change. And therefore, they propose different methods in parallel. And you can come up with a synthesis. There is not really a big difference. In my web pages, you can see that there is a section dedicated on comparison. And the section starts by saying these methods have several similarities. On the other hand, they are presented in the literature in a different way. They are presented in different books. They are presented in different disciplines. So it's important that you have clear the terminology, that you have clear what is the concept, what is the driving concept. And the driving concept is to look for robustness, to eventually look for opportunity, and to look for uncertainty in different manners, depending on how you estimated it. And there is an important concept that I want to emphasize here. These methods are called bottom-up, and they are distinguished from the left column, which is the top-down. The top-down is the method with which we started to analyze climate change. It's the method that we are still using in some cases. It starts from the climate scenarios. It starts from the hydrological scenarios for the future, and then uses a cascade of models to identify design variables, design projects in order to solve vulnerability, to resolve vulnerability, and to identify strategies. And this kind of approach has been recognized as extremely sensitive to uncertainty. And this is why research activities were stimulated in order to improve robustness, in order to define robust procedures. Because this top-down approach starts from something that is very uncertain, climate predictions, and then puts other models in cascade, and uncertainty is inflated. A last comment on the difference between the bottom-up approaches, robust decision-making, and decision scaling. We talked, you remember, about hydrological models, and I made an example, which is the linear reservoir. Linear reservoir, by the way, may be asked at the exam for the students, for the engineering students. Students who are not attending engineering degree programs will not be asked, as you know, these very specific questions, specific related to engineering, I mean. So we consider one hydrological model, one rain for runoff model, but I told you there are several different models. And in the same way, you may ask the question, why do we have several different models? Because the contexts are different. There are models that are more appropriate for a given case study. There are models that are more appropriate in other case studies. For instance, if you have a land that is very steep, you need a different hydrological model with respect to a land that is very flat. So you don't have to be surprised that basing on your case study, basing on the context, basing on the problem, you have several solutions, several possible methodologies to identify solutions. This is normal, and this is why very often I say, look, when we talk about climate change and the impact of climate change, we are talking of a very complex problem which doesn't have a unique recipe. This is why I question what has been said at the television in these days. We had 21 rivers flooding, and some people said we need more vegetation in the riverbeds. And I question these unique recipes. There are some rivers that need maybe a renaturalization, need more vegetation in the riverbed. There are other rivers which need a clear cutting of vegetation in the riverbed, really. It depends on the context. It depends on the individual mechanism. Again, for adapting to climate change, we cannot identify a unique recipe. In the same way, other people said we need reservoirs in order to store flood water and to store water for coping with droughts. Again, there is no unique recipe. In some cases, we may need reservoirs. In some other cases, we may use artificial recharge of groundwater reservoirs. In some cases, we may need a huge, big one reservoir. In other cases, we may need a distributed network of small lakes. It really depends. So you have different methodologies, different models, different alternative solutions, no unique recipe. Other people said we need to decrease the CO2 concentration in the atmosphere. You know, if you talk with a person that had the house flooded, and you say the problem is that we are releasing too much CO2 concentration, it is very likely that the person gets unhappy because, you know, they are looking for solutions, really. And they perceive that if we reduce the CO2 concentration, provided we can do that, I mean, the inertia of the system is very long. So it's not really a short-term solution. It's mitigation, it's not adaptation. In these cases, when these events happen, we need adaptation, plus mitigation maybe. But we cannot say that the solution, the real solution is reducing CO2. Yes, in the long term, maybe in 50 years from now. But in the immediate emergency, and in order to avoid the same disaster, we had 2 floods in 15 days, which means the same region, 2 floods in 15 days, which means that we need a urgent solution in the short term. Okay. Now, I want to give you some other example of some more information about what we discussed. So we talked about benefit. I go back some slides. Here, robustness and opportuneness were defined on the basis of a benefit function. Okay, benefit that I can retrieve from water resources availability. So benefit here was a criteria. I didn't say economic benefit, maybe also, environmental benefit. It was not really intended as money, but it's anyway a criteria, okay? And this criteria, this benefit function, was used to identify robustness and opportuneness here, and therefore it is used to take the decision. Now, in some cases, we need to use multiple criteria. It's not just one benefit function that drives our decision. So in some cases, we may have, for instance, as a criteria, the maximization of the economic benefit plus minimization of the environmental impact measured in some way. And therefore, you have 2 competing benefits, 2 competing criteria. Because if I want to increase usually the economic benefit, then I also increase the environmental impact. If my solution is a reservoir for flood protection or for coping with droughts, a larger reservoir gives to me a larger benefit in terms of the target that I want to achieve, but the larger reservoir has a larger environmental impact. So in some cases, we have to cope with, we have to use several criteria to drive our decision, no matter if the decision is taken with a top-down approach or with a bottom-up approach, no matter if it's taken with robust decision-making or decision scaling or infogap. we have several criteria, and the problem becomes more complicated, both in terms of seeking a compromise between people in the discussion, and indeed it becomes more complicated also from a mathematical point of view, because it becomes more complicated if you have, how can we compare two different criteria? What is called multi-criteria decision analysis is essentially a method looking for optimality of a compromise. And this is also called in the literature, this is just for your information, looking for a Pareto solution. And it's called Pareto. Pareto was a mathematician, and he proposed some formal mathematical methods to reach the best compromise, to identify the best compromise between different criteria. And it can be considered an optimization method. We don't go into the details. We don't look at the math. It's just enough for me that you know what is multi-criteria decision analysis, and you know the terminology Pareto solution. So you may find, for instance, in the quiz, a question, what is a Pareto solution? And the candidate answers may be a solution that seeks the best compromise between different criteria. Or the second answer may be methodology for building walls in an house, because, you know, Pareto in Italian is very similar to pareti, which means walls. Okay, so you will see some other alternatives which will be nonsense, but in order to identify what makes sense, you need to know. Okay, and this is just enough for me, because then I will give you another with more details in these last 2 hours. I want to introduce you another approach which allows you to deal with multi-criteria, with multiple criteria. And this will involve some math. It will be the last effort that I require to you. And this last method is different because while Pareto is defined in a formal mathematical way, the method that I'm going to discuss in the next hour is instead defined basing on a consultation with the stakeholders. Is still a formal mathematical way, but the information that is used by the method that we will explore is the information, the opinion of the stakeholders, is a method to weigh the opinion of the stakeholders. In the Pareto solution, just for your information, it's you that gives to each criteria a weight. So basically, the Pareto solution is a formal mathematical problem where you, as the engineer, as the responsible person, put together the several criteria by identifying priorities. So it's you deciding, for instance, that the economic benefit has the priority with respect to the environmental impact. So it's a top-down approach, while the priorities may be decided by the stakeholders. The stakeholders are the people who have an interest in decision-making and gives to you your opinion. So of course, the managers of the river managers, the responsible authorities for floods and droughts, prevention and mitigation will maximize, for instance, the size of the reservoir, while the environmental association will say, no, my priority is to minimize the environmental impact. Okay, so I think we can make the break now. Do you have any question for me before we make the break? There is one last thing that I wanted to tell you. There might be a question from those of you who are not studying engineering, like what can I find in the quiz regarding, for instance, InfoGap? And just another information that I need to give you. You have a test exam. The test exam is for engineers, and there is no test exam for non-engineering. And of course, the test exam for the engineers is a stress test for everybody. So, I mean, if you are a non-engineering student and you take the test exam, you can just decide to ignore the questions which contains maths. And this is the indication that I give to you. And the test is still useful because, I mean, you know that it's a test for engineering students, and therefore it is still useful, but it's not the type of question. I mean, the most complicated questions, you will not get them in your exam if you are not studying engineering. Just to be clear, during the exam, you will have two options to choose, and the exam for the engineers and the exam for the non-engineers in terms of quiz, okay? And of course, the non-engineering students will be checked based on I see your career, so I know what is the degree program, your degree program, and please make the right choice because otherwise you have to repeat it, okay? On the other hand, I want to give you an example. For instance, for InfoGap. InfoGap has a narrative in order to explain it and has some mathematics. When you see some mathematical relationship, it's the part which is more conceived to engineers. So non-engineering students will get questions on InfoGap related to the narrative. So what is the distinguishing feature, looking for opportunities and not only for robustness, and etc. They will not get questions on the definition of UH, on the definition of the robustness and opportunities. While an engineering student may get, for instance, in the quiz, this relationship here that you see on the bottom of the screen, and the question may be, is this a robustness function or an opportuneness function? Or the question may be, why do we look for the max in this equation with three candidate answers? Non-engineering students will not get specific questions on the math. Do you have any question for me? Okay, so let's take 15 minutes break. I leave you with on the screen the first slide that we will discuss in the next hour. Okay. So, the method which I mentioned to you in order to combine different criteria is called analytic hierarchy process, and it's a structured technique for handling complex decisions that contemplate multiple criteria. It has a quite long history. It was developed about 50 years ago. And the underlying concept is to decompose the decision problem into hierarchy, into a cascade of easier sub-problems, each of which can be analyzed independently. This is a general criteria when you have to deal with complex decisions, to try to decompose the complex decision into a cascade of simpler decisions. As I said, this method, AHP, analytic hierarchy process, bases the decision on the preferences that are expressed by stakeholders. We define stakeholders as the entities, which can be people, individual people, or administrations, or entity in general that have an interest in the decision, that are affected by the decision. And these entities clearly have opinions, have preferences, and this method tries to convert preferences into numerical values. So let's refer to an example. I think the best way to learn this process is to make a practical example. There are also examples in the web. I will give you links, but for the purpose of this, of our conversation, our discussion, I developed an example which is targeted on climate change adaptation and in particular water resources management. It can be easily extended to energy production. So we suppose that the decision on which solution is most appropriate for a given problem is taken in this case according to 4 criteria: net benefit, environmental impact, impact on the river flow regime, and CO2 emissions. So basically what we want is to maximize the net benefit while minimizing the environmental impact, while minimizing the impact on river flow regime, and also minimizing the CO2 emissions. Keep in mind that the identification of criteria in a multi-criteria problem, in general, the identification of the criteria that lead, that drive a decision is an essential step, which is to be carefully considered. So the first step of your decision is precisely what is leading to these 4 criteria. And the criteria has to be defined maybe with a conversation with the stakeholders. So there might be a preliminary discussion on what criteria should we adopt. Keep in mind that also in making this decision, there are some structured mathematical ways or mathematical recommendations that you may use. For instance, when you introduce criteria, you should avoid correlation between them, which means that if you, for instance, consider the environmental impact, it is questionable that you include also an impact on river flow regime, because they can be correlated. So we need a proper definition. What is environmental impact? Is environmental impact including the impact on river flow regime or not, because it's clear that if you introduce criteria that has correlated, you put more weight on these criteria. So, of course, if I include the environmental impact, and then the impact on river flow regime, and then I include air pollution, and then I include the CO2 emissions, I'm giving more weight to the environment, which may be fine, but on the other hand, you have to be aware of the potential biases that you may introduce in your decision. Now, we assume here that we skip this process. We have these 4 criteria, and we have potential solutions to solve the problem. And these potential solutions have to be evaluated against these 4 criteria. One important thing, when you have different criteria and you have to combine them, very often the available method propose to rescale the criteria in the same range, typically in the range 0, 1. Because otherwise, how can you compare them? If you express the net benefit, economic benefit, for instance, in terms of euros, and then you identify the CO2 emissions in terms of CO2 volume released per unit time, how can I combine different units? And therefore, the idea is to try to rescale this criteria in the range 0, 1. And then you can express them in terms of fraction of unity, okay? And this is called rescaling, rescaling in the same range of variability. Let me, before I discuss this slide here, let me clarify the problem. The problem is choosing a solution for increasing water resources availability. And we identify here 3 solutions. Again, identification of solutions is an essential step. We skip it here. And usually these solutions are identified again with a conversation with the stakeholders. Or if you want to skip the stakeholders, it's you, it's the engineer, it's the consultant that may take the task of identifying potential solutions. In this case, we deal with 3 solutions. We can build a dam, and therefore we increase water resources availability, we increase storage. Second solution may be reducing losses, because when you use water in irrigation or in civil use, in water supply for civil use, you have losses, you have leakages. And these leakages are very significant. If you look at the average in Europe of the leakages in water supply system for civil use, they are about, the losses are about ranging from 20% to 40%, which is significant. In agriculture, for irrigation, the losses are around 50% because there is infiltration of water along the canals that are used to bring the water to the fields, to the crops, and therefore you have significant losses. So there is a lot of research and a lot of investments in reducing losses. Another solution which is frequently used is precise irrigation. Precise irrigation means that you bring the water directly to the crop and you release to each crop the precise amount of water that the crop needs in that day, basing on meteorological predictions, basing on meteorological observations, and basing on the stage of growth of each crop. And there are indeed systems that can identify what is the precise amount of water, and systems, irrigation system that can release the water drop by drop, so reducing evaporation and reducing other losses that are originated by the fact that we don't irrigate in the most efficient manner. So we may have these 3 possible solutions, and from this cascade here, you can see that the problem, the goal is increase water resources. You have the 4 criteria here and the 3 solutions. And of course, each solution can be and must be evaluated according to the 4th criteria. So I have to if I make reference to the dam, I have to evaluate the net benefit given by the dam, the environmental impact, the impact on the flow regime, because a dam, of course, is changing the river flow regime, and the impact in terms of CO2 emissions, because building a dam and operating a dam entails CO2 emissions. The same for reducing losses. I have to evaluate the net benefit. So you see that there are connections from each solution to each criteria. And then, of course, I have to combine these criteria according to weight, which are indicated here as with the symbol W. And W is the weight that I have to assign to each criteria. So the way I combine the criteria is by giving weight to them. And therefore, once that I evaluated the 4 criteria for the dam, I combine them with the weights, and the value of each criteria for each solution is indicated here with the symbol N for net benefit, E for environmental impact, R for impact on the river flow regime, and C for the CO2 emissions. There is an index here, N1. 1 is the number of the solution, which is the dam, is solution 1. So for the dam, I evaluate N1, net benefit for the dam, A1, environmental impact for the dam, R1, impact on river flow regime for the dam, and C1, CO2 emissions for the dam. And then I can combine them, I can multiply them for the weight assigned to each criteria. And therefore, I can multiply W1 is the weight for criteria 1 times multiplied by N1, net benefit for the dam. And this gives to me a first contribution to the overall score for the dam. Weight 1 for the net benefit of the dam gives the score, the first score for the dam. Weight 2, weight for the environmental impact times the environmental impact of the dam gives the score contribution for the solution dam according to the second criteria, environmental impact. And then W3, weight 3 for R1. 1 here is solution 1, the dam, R is impact on river flow regime. And then W4, weight 4 times C1, CO2 emissions for solution 1, which is the dam. And then I sum these 4 contributions and I get an overall score for the dam. I make the same thing. Here you don't see the symbols because otherwise the figure will become too complicated. I make the same computation for the solution reducing losses and the same computation for the solution precise irrigation. And then I can see what is the solution that has the highest score. Okay. And the score again is given by, for the dam, W1 times N1 plus W2 times A1 plus W3 times R1 plus W4 times C1. And this gives to me the score for the dam. In order to make this computation, however, I need to estimate the 4 weights, and these are to be estimated with a discussion with the stakeholders. And the discussion has to identify the weight based on their preferences. So I need the 4 Ws, and I need for each of the possible candidate solutions, dam, reducing losses, and precise irrigation, I have to estimate the value of the 4th criteria. So for the dam is N1, E1, R1, C1. Okay. For reducing losses, it will be N2, E2, R2, C2, and so forth. So for each of the candidate solutions, I have to estimate the 4 criteria in a scaled manner. Each of the criteria has to be expressed by a number which is varying from 0 and 1. So let's focus on the criteria, computation of criteria for each solution. I move to the next slide. It can be done through utility functions. What is a utility function? And this is an important concept that we are introducing, which is also essential for non-engineering students. Okay, the utility functions assigns to the values of each criteria a corresponding value in the range 0, 1. So, for instance, in terms of economic benefit, I consider all the possible economic benefits that I can reach with any solution, and I transform them in the range 0, 1 with some constraints. So to the minimum of each criteria. So for instance, to the minimum benefit, I give utility 0. Because if I want to rescale a number, a series of numbers in the range 0, 1, a possible solution is that to the minimum of these numbers, I give a value of 0. And to the max of these numbers, I give a value of 1. So these are the two first constraints, okay? So 0 to the minimum, 1 to the maximum. And then I have a third constraint. Increasing utility is assigned to the values corresponding to increasing convenience. So when I move from 0 to 1, I have to assign increasing values to increasing criteria values. So one possibility is the linear function. Here, the linear function, which is depicted in this figure that you see on the screen, gives 0 to the minimum value of the criteria. In this case, on the graph, the minimum value is 0. Look at the horizontal axis. The horizontal axis is varying from 0 to 20. So this is the range of this criteria, which I want to scale between 0 and 1. So I give to the minimum, which is 0, utility 0. I give to the max, which is 20, utility 1. And the progress from 0 to 1 is linear. In general, we deal with nonlinear utility functions. But in this case, to provide an example, this is a simple way, if you don't have any information, to compute utility. So for instance, think of the dam. The dam, and think at the other solutions in terms of net benefit. I go back to the previous figure. Think at the three solutions, the three pink rectangles in the bottom of the figure here, and think at the net benefit. So the dam will have a net benefit. Reducing losses will have a second net benefit. Precise irrigation will have a third net benefit. So I have three possible values of the criteria. I give to the minimum net benefit the value of utility 0. I give to the max of the net benefit utility 1. And to the net benefit in between, I make a linear interpolation between 0 and 1, and between the min and the max benefit, according to this utility function. So this is a very easy way. On the other hand, there are more structured methods in order to identify what is the progress of utility depending on the indicator. So let's, for now, be happy with this very easy solution. It's what is called very frequently linear rescaling. It can be applied to any of the criteria. And in this way, for each solution, we estimate the 4 criteria, and we rescale the 4 criteria through the utility function in the range 0, 1. Okay, we solved the first problem. Okay, in a very simple way. Just be aware that there are more structured ways of elaborating this utility function that you see on the screen, which is not necessarily linear. Okay, good. Now let's focus on. Yeah, please.
Can I ask something?
Yes.
So instead, in the case of CO2 emission,
Yeah.
emissions, for example, we have to assign 0 to the minimum value
Yes.
of
We
the
have,
emission.
no, you have to
No,
assign.
sorry, to the maximum value of the emission, and
Yes.
1 to the minimum.
Yes, perfect. You're perfectly
Okay.
right. Yeah, perfectly right.
So at the end, the overall score of a solution is a measure of its convenience, not of its impact. So
Yes,
the
it is
okay.
a measure, an overall measure of convenience related to the fourth criteria. So if the fourth criteria include the impact, environmental impact, for instance, it also reflects a measure of the impact. It depends on the weight that you give to the criteria. For instance, if you go back here to the fourth criteria, you may give weight 1 to the CO2 emissions and weight 0 to the other 3 criteria, which means that you are deciding basing only on CO2 emissions. And in this case, depending on the weight, you also minimize the impact. And I didn't explain how the weights are identified yet. But you will see that if you want to give more weight to the CO2 emissions, you have to play with the weights. Is it clear?
Okay. Okay. So okay. So at the end, if a solution have a high score, is a good thing. Not a
Yes,
bad thing.
yes, yes, of course, because in any case, the utility function is computed as you suggested. So for the CO2 emission, we give utility 1 to the minimum value of CO2 emissions. And therefore, in this case, the straight line that you see on the screen now will have a slope that is negative, not positive, which means that the highest score will correspond to the lowest emission, which is what you want.
Okay. Thank you.
Yeah, no problem. Now let's focus on the weights. Okay. So the question here is, I have 4 criteria. How can I assign the weight to each of them? Now, first of all, by definition, weights should sum up to 1. Okay. So the 4 weights, if you want to give equal weights to the 4 criteria, the 4 weights have value 0.25. Okay. If you give value 1 to one weight, it means that the other weights are 0. So the sum of the weights is 1. Okay, this is a general definition. And then you have several options. What I'm explaining now to identify weights is just one of them. And I want to make a premise here. How do we estimate weights in this case? By consulting with stakeholders. So we have to get their opinion, okay? And their opinion is, as you will see, collected with a structured process, which is very transparent. On the other hand, as you will see, this method for putting together the opinion of like 100 stakeholders is a bit based on mathematics. So it's a little bit, complicated, and it's complicated to ensure an objective approach. So it's complicated, as you will see, for the sake of ensuring objectivity. On the other hand, when you adopt a complicated process, this is a general consideration that you have to take into account. The transparency of the decision may get undermined. So if you propose a theoretical model that is complicated, like, for instance, InfoGap, and you want to explain it to people, it's not easy. You see that it's not easy also for me to explain to you, and you are trained persons, you are persons that are prepared on mathematics, statistics, etc. If you present it to persons that are not expert in mathematics and statistics,
it may look obscure. When something is obscure, when the people, the stakeholders perceive something as obscure, keep in mind that the efficiency of the decision process is undermined. We need to be very clear in explaining how the process works. The analytic hierarchy process, from this point of view, is a little bit risky. And therefore, I want to make this premise. I'm trying to explain it to you in a rigorous manner, so I need to refer to the math. On the other hand, try to make an effort to get the concept of it, because the concept is very simple. The concept is, I ask people their preferences and I put them together with multiple criteria. It is very easy if you have just two criteria. You get the stakeholders and you ask their opinion, and then you make an average, okay? Like, okay, the criteria are CO2 emission and net benefit. Okay, 50% of the people wants to give equal weight to all of them. 10% of the people want to discard the net benefit. 10% of the people want to discard the CO2 emissions. It is quite easy if you have only two alternatives, like to compute an average, to seek a compromise. In this case, we have four criteria. It's very complicated to estimate an average. And therefore, what is the solution? The solution is, when you have to compare four criteria, like in this case, let's compare them 2 by 2. Let's reduce the complex decision in a sequence of easier decisions. And let's compare them according to this scale of preference. You see the table on the screen. So, for instance, let's compare the net benefit with the CO2 emissions. And the net benefit is the first term of comparison. CO2 emission is the second term. So, do they have equal importance? So, let's give to the net benefit with respect to the CO2 emission the importance 1. Is net benefit moderately more important than CO2 emissions? Okay, let's give to net benefit score 3 with respect to CO2 emissions. Is the first criteria strongly more important than the second criteria? Let's give to the first criteria with respect to the second score 5, and then so forth with 7 and 9. This scale is completely arbitrary. The proposer of analytical hierarchy process proposed this scale from 1 to 9, and you can also give numbers in between, like 2, 2.5, in order to reach a compromise between the stakeholders. You have to convene the stakeholders and say, okay, let's discuss the importance of net benefit with respect to the CO2 emissions. Okay, and then you make an average, okay? And if the average among the stakeholders is 2.9, that's fine, okay? And it is easy to compute the average because you ask the same question to all the stakeholders and you just say, okay, what is your opinion? It's 1. What is your opinion? It's 9. At the end, you compute the average. And then you may question whether the average is a good indicator. But in any case, this is a possibility, very clear. And then you may ask the same question by reverting the orders of the criteria. What is the importance of the CO2 emissions with respect to the net benefit? If the previous decision was that the importance of the net benefit with respect to CO2 emission is 3, when you ask the dual question, what is the importance of the CO2 emission with respect to the net benefit, the score is already computed, is 1/3. It's the reverse of it, okay? And it's important to say that you may ask the same question in a different manner. First criteria against the second, or second criteria against the first. But of course, the two decisions must be coherent. So if the first reply is 9, the second reply is 1/9, 1/9, etc. Okay? And then you repeat the same thing for all the couple of criteria. Net benefit with respect to river flow regime. You make the same question. And what you obtain is a matrix. Let's suppose that you get this. if you compute net benefit with net benefit, of course, they have the same importance. It's the same criteria. So on the diagonal, you have a list of ones. It's a diagonal matrix. No, it's not a diagonal matrix. It's a matrix with ones, units in the diagonal. Okay. And then if the net benefit with respect to the environmental impact has a score of 7, the opposite element in the matrix has to get a score of 17. If the net benefit with respect to river flow has a score of 4, then the opposite one must be 1/4. Again, if the net benefit with respect to CO2 has a score 5, the opposite one is 1/5. These numbers are purely indicative. It's just a guess. You can revert the order. If you want to give more score to the CO2 emissions, this is fine. I mean, you can devise the matrix as you want. On the other hand, you have to respect the fact that in the opposite position, you have to place the inverse of the value that you just computed. And on the diagonal, you have to put 1. Is it clear? Is it clear that this is very easy? I mean, I can ask the same question to you, compute the average, and fill the matrix. It's no problem. We can do that. It is very easy. But do you have any comment on this? Because you should be able to see that there is a potential flow, a potential mistake, a potential error in assigning values to this matrix according to the stakeholders' opinion by only respecting the constraints that I mentioned. Do you see a potential gap in this procedure? If I tell you one term, consistency, do you get any input in order to identify the potential gap? Yeah, maybe. Why?
Situation to situation, you arbitrarily choose the weights depending on the context.
Yeah.
And you cannot compare between different situation and approaches. I don't know how to.
I'm not sure if your answer is correct. I tell you what is my concern, and then let's see if the same your concern. My concern is that if I just carry out this sequence of comparisons arbitrarily, I may identify, for instance, that the net benefit with respect to the environmental impact has an importance of 7. Yeah? There is a comment from the audience. Yeah, please.
I start with the net benefit 1, and then I say environmental impact is way more important. But then in the matrix, I compare the environmental impact with the river flow regime.
Yeah.
So that might be.
Yeah. Okay. Yeah, you are correct. So if I say that the net benefit has a score of 7 with respect to the environmental impact and a score of 4 with respect to the river flow, it means that the environmental impact is less important than the river flow. So when I compare the river flow with the environmental impact, I need to make sure that I am consistent with the evaluation that I made. So let's see, environmental impact with respect to river flow is more important. So here, am I consistent or not? I'm not sure I am consistent here because yes, I am consistent because I made a mistake earlier. So if the net benefit is much more important than environmental impact and is a bit more important than the river flow, it means that the river flow is more important than the environmental impact.
So when I go here, river flow, environmental impact, 1/4, I'm not sure it is consistent. Okay. So basically, when I make this comparison, I have to try to remember what is the result of the previous ones in order to make sure that everything is consistent. Fortunately, this is very complicated because if you have like 20 criteria, it's very complicated to take, to keep the track of what are the previous steps. Fortunately, we have a mathematical procedure that allows us to check whether or not the matrix is consistent, fortunately. And this is a mathematical procedure, so it's very objective. It is a test. If the test fails, we have to go back and change it. And the problem of this test is that it's a bit complicated. How to compute this test, how to perform it. And another question, how to estimate the weights from this matrix. So if the test is passed from this matrix, how can I estimate the weights? So let's reply to these two questions very quickly. And then on Thursday, I'll go back a little bit, okay, in order to make sure that you digested it. So, yeah, a question here.
If I read the first row, second column, I say environmental impact is way more important than net benefit. And then I go to the next, to the third column, first row, and say river flow regime is more important than net benefit. Or where's the comparison? Do I read the second row that the environmental impact, no, that the river flow regime is more important than the environmental impact, or the other way around?
Yeah, I understand what you mean. I understand what you mean, and let me think yeah, the question is basically, when I look at the first row gives, puts as first place of the comparison. For instance, for the number 7 in the first row, the first one is environmental impact or is net benefit? This is your question. So basically, a score of 7 here means that it's net benefit more important than the environmental impact, or the other way around.
Yeah.
Okay, let me think if this is relevant. So net benefit. Yeah, I think, just 1 second. So if I put at the first place the column, let's say, so if I put at the first place environmental impact with respect to net benefit with a score of 7 is much more important. This is less important, and therefore it means that river flow with respect to environmental impact is less important. So when I look river flow to environment, I don't think it makes a difference actually.
But you assign the importance of the of a specific criteria. So
yes,
it would mean that I switch the importance.
Yes, but it doesn't matter provided you keep them coherent in your matrix. So my approach is I put at the first place in the first row the criteria in the column. So, okay, net benefit with respect to net benefit in the first row is same importance, is 1. There is no question on that. And then I take net benefit with respect to environmental impact, and I put the net benefit in the first place. So net benefit is more important, much more important than the environmental impact, and is a bit more important than the river flow. So the consequence is that the river flow is more important than the environmental impact. And then I move with the other lines with the same order. And I see that in this case, the matrix is So let me see. I said that river flow is more important than environmental impact, and then when I see river flow with respect to the environmental impact is 1/4, I think this is not very consistent. Okay, this is not very consistent. But I mean, it's clear that the matrix can be non-consistent. The important thing is to have a test available to test it. Because as you see, to check consistency, even in this quite simple case, is not easy. It's easy to get confused. So we need a test. So first of all, how to compute the weights? It is easy, but it's not easy to be explained. Basically, the weights, if you look at this matrix, you can compute the weights anyway, even if it's not consistent. So let's focus on the weight computations. The weights are the values in the matrix principal right eigenvector. So this is something that goes back to your studies on basic maths. What is an eigenvector? A right eigenvector of a square matrix. And I can tell you that it's in R and Excel, it's very easy to compute them, to compute this right eigenvector. And this right eigenvector have to be rescaled to give a sum of 1 because the weights have to sum up to 1. So once that you have the matrix in Excel, you take the right eigenvector and you have a function to do that. Rescale the elements of the eigenvector to 1 and you get the weights. This is something very easy. Also in R, you have a function to get the right eigenvector. It's very easy. If you want to understand what is the mathematical meaning of what you're doing, you have to go back to your basic studies in maths. Maybe that you remember better than me what is a right eigenvector. I don't want to get into these explanations now because it's out of our level of detail that we want to reach here. What I would tell to stakeholders is just that basing on the matrix, I have a procedure that is assigning weight, and what I would tell to stakeholders is try to get your feeling of what is the result of this matrix. What are the criteria that are more important? We expect that these criteria get a larger weights. Let's see if indeed the right eigenvector gives the larger weights to these criteria. So I would focus on the intuition, and if I want them to better understand, I would start with a very simple situation where I give the max of the score to net benefit or to CO2 emission to one criteria, to the other criteria. I put all of them at the same level, and then I make the computation and I show that indeed the criteria where I put the max score gets the highest weight and the other criteria get the same weight. So I would propose a very simple example to show in practice that the weight matches their expectation. For instance, I could provide an example with only 2 criteria. And then I compute the matrix with only 2 criteria. It is very easy. And I compute the right eigenvector and I show that with 2 criteria, I give the max of the importance to 1, and the second one, I give a very reduced score, and I show that we are getting what we are expecting. And then I can move to a more complicated solution. So I wouldn't try to explain to stakeholders in terms of maths, but I would explain to them by making a very simple example, introductory example. With you, I adopted the midway because 4 criteria is, yes, it's simple, but not so easy, okay? And now let's stop here, and the check of consistency, which is similar situation, so a mathematical procedure that it's not easy to be explained in terms of mathematics, but it's easy to explain in terms of providing a simple example. It's more or less the same thing.
we will get into the details of it on Thursday. Do you have any question? Okay, good. Thank you very much.